In 1905, Einar Hertzsprung and Henry Norris Russell did something pretty cool. They were able to measure the distances to several stars, and using those distances, they were able to calculate the absolute magnitudes of those stars, their true brightnesses. And then they plotted those magnitudes against the spectral class of the stars, the color of the stars, and the result was amazing. We call this a Hertzsprung-Russell diagram, or an HR diagram. Here's the HR diagram that Russell published a few years later in 1917. You can see across the top the spectral classes of the star. Be a fine girl, kiss me. At the left-hand side, you can see the magnitudes of the stars on the vertical scale. At the top, they're very bright. At the bottom, they're very dim. As we go across the top from left to right, the stars are bright blue at the left and they are dim at the right. Now, look at that grouping of stars that crosses from the upper left to the lower right. That's called the main sequence. Imagine the chill that must have gone down their spines as that line showed up on their diagram. What is the significance of that line? Why is it that the luminosity of stars and the color of stars has such a simple relationship? So here's what that HR diagram looks like when you include 22,000 stars whose temperatures, luminosities, and distances have been measured to accuracies that Hertzsprung and Russell could only have dreamed about. You can see that the spectral class has been changed to temperature. The color is now related to the temperature of the star. That's the surface temperature. Now, look at that main sequence. It's still there. It's a little wiggly, isn't it? But it's still that line, that nice line that goes from the upper left to the lower right that shows that temperature and luminosity are positively correlated. But then what's this funny branch off here up to the upper right? That shows a negative correlation. Those stars seem to get brighter as they get cooler. And then look at this weird curve down here at the bottom of a bunch of impossibly dim, yet very, very hot stars. What's up with all that? The main sequence is composed of stars that are fusing hydrogen into helium within their cores. Since that's what most stars are doing most of the time, the main sequence has the most stars in it. Hertzsprung and Russell knew nothing of nuclear fusion when they did that first scatter plot. Nevertheless, what they found in that line that goes from the upper left to the lower right is the signature of hydrogen fusion. Let's track the sun as it wends its way through the HR diagram. It starts here on the main sequence, sedately fusing hydrogen into helium in its core. Our sun will spend 10 to 12 billion years happily sitting right there. Oh, it'll gradually slide a bit over to the left as its temperature slowly rises, but that motion is insignificant on this scale. The big change comes 6 billion years from now when it runs out of hydrogen in its core. The core will contract until a shell of hydrogen surrounding that helium starts to fuse. The outer envelope, the gases that surround the core, will expand by a factor of 100, and our sun will quickly slide over here to join all the other red giants. But that hydrogen shell keeps dumping more and more helium onto the core, and eventually the pressures and temperatures in the helium core are sufficient to cause it to start fusing into carbon. And the sun slides horizontally over to join all the other end-stage hot red giants. Now things start happening pretty rapidly. As the helium in the core is exhausted, the core contracts again until helium near the carbon core can start to fuse in a shell. The sun slides horizontally back over to the cooler red giants. But it can linger there only for a short time because the core has become unstable and has started to eject the envelope of gas that surrounds it. As the ejected gases begin to disperse, the sun will shine forth as a planetary nebula. But also, the intensely high temperatures in this tiny core will begin to leak out, and the sun rapidly moves horizontally to the left. As the envelope disperses even more, the sun becomes less and less luminous, so it begins its downward slide to join the white dwarfs. And now, with the envelope completely dispersed, the core, which is now a diamond the size of the Earth, begins its long, slow slide down that final curve as it gradually cools. Isn't it amazing what you can learn from a simple scatter plot? The relationship between two seemingly unrelated variables can hold a wealth of information.